So, okay, so we have seen that the expression for two area interconnected system, this is frequency at steady state, and this is the type power flowing from 1 to 2, the steady state values. And we have seen one special case when disturbance was in area 1, right, and area 2 it was 0, and area capacity same for both the areas. So, we took A1 to is -1 and we choose R1 is equal to R2 is equal to R, right, and subsequently by considering delta PL1 is equal to 0.01, delta PL2 0, A12 is equal to -1, and D1 D2 are neglected, and R1 is equal to R2 is equal to R taken 2.40 Hertz per unit megawatt, and we showed, we have seen that what will be the frequency error, steady state error of frequency, and what will be the tie line power flow, that has been done, right. Now, another next is the tie line frequency bias control, right. So, that means these two equations 38 and 39, it suggests that if your system is uncontrolled, then there will be an error in your steady state error of frequency deviation as well as your tie power deviation following a load disturbance, right. So, in that case we have to bring back this to system frequency to its nominal value, that means delta FSS deviation has to be 0, and tie power also steady state flow something is there. So, here also we have to bring back to its scheduled power flow such that delta P tie 1 to SS will be 0. Because of this reason we go for tie line frequency bias control. So, that means equation 38 and 39, just the previous two equations suggest that there will be steady state error of frequency deviation and tie power deviation, which I told you, right, following a change in the load. Now, to correct this steady state error, supplementary control must be given in both the areas. Supplementary means a integral control action. The supplementary control in a given area should ideally correct only for changes in that area. That means, suppose you have a two area system, and in area 1 suppose load disturbance is area 1, right. So, it should accommodate its load in its or what you call area 1, whatever power generation here, it should accommodate its own load, right. Of course, I told you that if it is not, then it has to borrow powers or purchase power from the other areas, right. So, supplementary control in a given area should ideally correct only for changes in that area, right, that is the concept. So, if it is so, in other words, if there is a change in area 1 load, there should be supplementary control action only in area 1 and not in area 2. That means, whatever it is, that area 1 supplementary control action actually what we call will be only in area 1 if there is a load disturbance area 1, but not in area 2, that is the philosophy. Now, equation 38 and 39, those equations for delta f SS and delta P tie 1 to SS, right, indicate that a control signal mode of tie line power flow deviation added to frequency deviation weighted to a bias factor would accomplish the desired objective, and this signal we call known as area control error, because each power system in each area you have your what you call the steady state error in frequency as well as tie power, right, deviation and frequency deviation. So, if there is no controller, there will be a steady state error, right. So, this control signal actually we call as area control error or ACE in short form, right. Now, what is ACE? The area control error for area 1 actually and area 2 can be defined as AC1 will be B1 delta F1 plus your delta P tie 1 2. We have seen no steady state error in general for frequency, that is your delta FSS, say for isolated system, right, it is basically minus your delta PL upon your D plus 1 upon R, right, that we have seen, and D plus 1 upon R we are calling say B1 or beta 1 frequency response characteristic, right. So, that means this frequency this bias factor, this B1 or B2 or in general B parameter is called frequency bias constant, right, this is a bias factor. So, AC1 is equal to B1 delta F1 plus delta P tie 1 2, this is equation 40, and AC2 is equal to B2 delta F2 plus A12 delta P tie 1 2, because it is B2 delta F2 plus delta P tie 2 1, and delta P tie 2 1 is equal to A12 into delta P tie 1 2, which we have seen before, right. Now, where B1 is equal to beta 1 we call beta 1 beta 2 we call frequency response characteristic, that is B1 is equal to beta 1 is equal to D1 plus 1 upon R1 for area 1, and B2 is equal to beta 2 is equal to D2 plus 1 upon R2, this is for area 2, this is equation 42, right. So, this is actually B1 and B2 value. Now, let us see. Now, B1, beta 1 and beta 2 are the frequency response characteristic of area 1, area 2 respectively. This we have seen in general, that steady state error I told you it is minus delta PL upon your D plus 1 upon R. So, beta is equal to D plus 1 upon R is called area response, your what you call frequency response characteristic, right. So, that is why and this is for area 1 and area 2, that is why beta 1 and beta 2 we have taken, right. So, now this control signal AC1 will be basically then delta F1 will come into B1 and this is delta P tie 1 2 and output is AC1. This AC1 will go as an input to the integral controller for two area system. Just hold on, for two area system, right, that we have seen the your what you call the block diagram, and in this case your just let me see this block diagram. This block diagram, this is U1 and this is U2, right, and this U1 actually this U1 and this U2. That means from here, I mean if you draw this here from here, that this is the delta F1, this is delta F1. From here this delta F1, then make a B1 and summing it up, and this side you take the delta P tie 1 to 1, and this is actually your what you call that your delta P tie 1 2, and this is I am making it for you, right. For example, just see that here for area 1, right, hope it will be accommodated. Area 1 I am making it for you, right. This is your for area 1, this is your B1, right, and here you put that summation symbol, this is plus, right, and this is your U1, and this side from here it will come that your tie power, because this is your tie power. So, and here it is your this thing what you call plus, and this is your delta P tie 1 2. So, this is actually delta P tie 1 2, right, and that means this one actually is AC1, this output is this one, look this output is AC1. So, this is your AC1, right. Similarly, that delta P tie 1 2 making by green ink, this is your A12, right, because this is delta P tie 2 1. So, it is A12 into delta P tie 1 2 actually, right. So, here you that your this is actually delta P tie 2 1, delta P tie 2 1 is equal to A12 into delta P tie 1 2, and frequency will come from here. This is your B2, this is your B2, and here it is your B2 into delta F2, and this is your plus, and this part actually your AC2, the output is AC2, right, and integral control action is there. So, here we are putting your what you call this is integral action is your here integral action. I am just making it short because of this is integral control action, and this where we are putting say this is U1, right, and similarly here also integral action is there, here also integral action is there, that is basically minus Ki upon S, integral action is there, and this output is U2, right. So, this portion actually this is U1, here I have cut it for you, right, this is U1 out, this is integral control actually, this part actually minus Ki1 upon S, here it is minus Ki1 upon S, and this is actually minus Ki2 upon S. So, this is actually minus Ki2 upon S, here it is shown, right. So, this is integral controller, this is integral controller, there is a controller block, this is actually controller block, right. Because of space, because of this page and this space limitation, I could not put here minus Ki upon S, minus Ki1 upon S, and this input to this controller is AC, input to this controller is this your what you call here it is AC2, right. So, this is actually your AC2. So, that is why your what you call this input to this your AC2 and input to this controller is AC1. So, that is why here we have made it that this thing your this one that AC1 going to the integral controller to U1, and this is AC2 going to, and this is your delta P tie 1 to what I have shown in that block diagram, right. So, that means the integral control is this. Now, this is integral control of for area and area 2 is given by. So, U1 is equal to minus Ki1, this is an integrator. So, it will basically minus Ki1 integral of AC1 dt, this is equation say 43, and u2 will be minus ki2 integral of AC to dt. This is equation 44, whereas ki1 and ki2 are the integral gain settings for area 1 and area 2 respectively. Now, question is that what value of ki1, ki2 will choose and those things, but this ki1, ki2 all can be optimized, right, but those are beyond the scope, because in the classroom we cannot do that because you need simulation. So, no need actually, just for the your u1, but your is equal to minus ki1 integral of AC1 dt, and u2 will be minus ki2 integral of AC2 dt, and ki1, ki2 your what you call the integral gain setting, and for the system we have chosen. So, actually if we take integral square error technique or so, this ki1 or ki2, if because it is equal area system, if we assume these are equal area system, this is equal area system, that means both the areas are the you have the same rated capacity, equal area, I mean A12 is equal to minus 1, if it is so, right. But then your if you opt, then gain setting also ki1 is equal to ki2 is equal to ki. If it is equal area, that means both equal area means both the areas have identical generating units, both the areas have identical generating units, right, and your what you have same capacity, this area and this area, if this is 1000 megawatt, this is also 1000 megawatts, right, and both having the same identical units, identical rating, then only we can make ki1 is equal to ki2 is equal to ki, same integral gain setting, right, same integral gain setting. But if this is a, for example, say if this is non reheat type turbine, here it is reheat type turbine, then ki1 and ki2 will be difficult, even if the rating of both the areas are same, because the units are different. And even for that means if whenever you are considering ki1 is equal to ki2 is equal to ki, that means this one actually your what you call your equal area system and identical units in the both the areas, right. So, that means your this for this two area system, actually if you take ki1 is equal to ki2 is equal to ki for this system with the standard parameters, right, parameters I will give you later, standard parameters, right. If you see that, we will find ki1 is equal to ki2 is equal to ki, if they are equal area, then it will give you more or less good result for value of ki is equal to 0.7, say roughly 0.7, right. So, this is actually how one can take that integral control action, right. But here also one can try with proportional integral or PID, but for thermal units actually PID control is not recommended, right. So, proportional integral is possible, and second thing is I told you this area control error, right, actually it is not fed to the controller continuously, it has a sampling time, your what you call, you have to your sample at every sampling instant. For example t is equal to 2 seconds, right, and this is not shown here, and accordingly you have to evaluate u, because any system is any system you take, in reality that it is a basically continuous system, only controller part will be in your what you call in discrete domain, whereas this system, this whole system, this thermal system, whatever it is in continuous system, right, but controller you will find in discrete domain, but for the analysis simulation those things are slightly different, but beyond the scope of this course, right. So, all these things that area 1 and area 2 I showed. Now, next is the basis of our selection of bias factor, that means B1, this B1 and B2, there should be some criteria for selecting, right. One thing I can, before proceeding further, I can tell you that B1, B2 or your in general B value cannot be less than beta. That means this B value that frequency bias, it cannot be less than beta, it cannot be, right. This question I am putting it to you, and if you can suggest the technical reason why it is, then I will appreciate that. I will show you B greater than beta, B is equal to beta, but B less than beta is never possible, I mean it is not recommended, it is not at all recommended. That means, and beta is equal to your D in general D plus 1 upon R, right. So, B value it cannot be less than D plus 1 upon R, it cannot be less than that, right. So, this is a question to you, and if you can answer this I will appreciate that, but it is not recommended. So, now next is that basis for selection of bias factor. So, from the point of view of steady state performance, the selection of bias factor is not important, right. As far as steady state are concerned, steady state performance is concerned, so bias factor is not that important, right. But for any combination of area control errors, containing components of tie line power deviation and frequency deviation will result in steady state your restoration to the tie line flow and frequency, since the integral control action ensures that AC is reduced to 0, right. This will happen, AC will be reduced to 0, that is true, right, for any control, any integral control action is there, but you have to select some reason should be there, that what will be the frequency bias characteristic. Generally B is equal to beta is recommended value, right. Now question is, consider the following area control errors applicable for a 2 area power system. Suppose AC, we know AC is equal to, we know that we have seen that is your B1 AC1 is equal to B1 delta F delta F1 plus delta p tie 1 2. Now what you can do is, suppose AC1 steady state value multiply by some constant A1, capital A1 into delta p tie 1 to SS plus B1 into delta Fs is equal to 0. This is equation 45, because your whenever you put integral or supplementary control action, AC1 steady state will become 0. So that is 0, but this is A1 into delta p tie 1 to SS plus B1. A1 A2 is some, A1 is some constant. Similarly, AC to steady state is equal to capital A2 into small a12, that is the area capacity ratio, into delta p tie 1 to SS plus B2 delta Fs is equal to 0. This is actually equation 46, right. This A1 A2 some two constant we have taken arbitrary, right. The above equation result in delta p tie 1 to 0 and delta F is equal to 0 for non-zero values of A1 A2 B1 B2. I mean, if you choose some value of A1 A2 and B1 B2, right, and if you feed that area as an area, I mean what I want to mean, that area control error AC1 you can take A1 delta p tie 1 2 plus B1 delta F. Similarly, AC2 you can take A2 A1 2 delta p tie 1 2 plus B2 delta F, and if you once you and choose some realistic value of A1 A2 and B1 B2, then what will happen, that you will find the steady state value of AC1 and AC2 both will be 0. I mean, in the integral control will ensure that, right. If you put, that means, however, the composition of AC signal is more important from dynamic performance consideration, right. That means you can put here A1 A2 some values, but you can see during dynamic response during its transient imbalance, no, that your AC1 AC2 same at the same time delta p tie 1 2 and delta F1 delta F2 you have to check their transient behavior. One thing can happen, it may take long time to settle, right, and maybe peak deviation will be much higher. So that is why that composition of AC signal is more important from dynamic performance consideration. I mean during transient imbalance, right, at steady state both are becoming 0. So this can be explained by considering the transient response to a sudden increase in the load, say in area 1, right. So the sudden increase in load will result in a decreases system frequency. This you know, if load increases, frequency decreases, followed by the governor response, right, which limits the maximum frequency excursion and subsequently brings the frequency deviation back to a value determined your what you call by the your regulation characteristic of both system, that is regulation characteristic means that is R1 R2, the regulation parameter in the area 1 and area 2. So we can write the steady state value if delta PL2 is equal to 0, if delta PL2 is equal to 0, then here in area 1 only load has increased and delta PL2 0, then delta FSS is equal to, right, delta FSS is equal to A1 to delta PL1 upon D2 plus 1 upon R2 minus A1 to D1 plus 1 upon R, putting delta PL2 0 in equation 38. So we get this one, right. So if we assume the equal area your equal area capacity, that is PR1 or PR2, something we have seen in just in the previous slide, right, that A12 is equal to minus PR1 upon PR2 is equal to minus 1. So if it is so, then you put it here, this is actually beta 2 and this is actually beta 1, right. Beta 2 is equal to D2 plus 1 upon R2 and beta 1 is equal to D1 plus 1 upon R1. Now if you put it here, then you will become this will become actually equation 47 actually reduces to delta PFSS is equal to minus delta PL1 upon beta 1 plus beta 2. So this is equation 48, right. So at this point there will be deviation of tie power flow from its scheduled value, because it is frequency is showing the steady state error. So naturally tie power also will have this steady state value, right. So supplementary control which is much slower than the primary speed control means the regulation parameter, right, and supplementary control which is it comes your what you call actually it action starts. So, in primary speed control parameter action is over, right. We will now commence responding. So, if that means it is a slow process, right. If it is so, then we will what you do, we will consider few cases. Let us now study the your following. One is case 1, say case 1 case for B1 is equal to beta 1 and B2 is equal to beta 2, say delta PL2 is equal to 0, A12 is equal to minus 1 and AC1 SS is equal to delta P tie 1 to SS base plus B1 delta FSS, right. Now, using this condition that you will get this one. How will get this one? Just I am showing you how we will get this one. Just hold on. So, what you will get actually, we know this expression delta FSS is equal to A12 then delta PL1 minus this one, right, divided by your D2 plus 1 upon R2, right, minus A12 D1 plus 1 upon R1, right. Now, we know this this is actually beta 2, this is actually beta 1 and we have taken here B1 is equal to beta 1, B2 is equal to beta 2 and delta PL to 0 and A12 minus 1. So, if you substitute here, this is actually your beta 2 and this is actually your beta 1. So, B is equal to B2 is equal to beta 2 and B2 is equal to B1 is equal to beta 1. Now, that means delta FSS then will become delta PL2 is equal to 0. So, A12 is minus 1. So, it will become delta PL1 by beta 2 plus beta 1 because A12 is minus 1. So, it will be plus. So, it is delta FSS, just now we have seen this minus delta PL upon beta 2 plus beta 1. Similarly, for tie power case also, tie line power case, if you just see this one that delta P tie 1 to SS, delta P tie 1 to steady state, right, is equal to, actually we got this expression D1 plus 1 upon R1 delta PL2 minus D2 plus 1 upon R2 your delta PL1, right, divided by the same numerator denominator, right, same thing. So, this one your D2 plus 1 upon R2 minus A12 D1 plus 1 upon R1, right, putting delta PL to 0 and this is your what you call beta 2 and this is beta 1 and A12 minus 1. So, this will become actually delta P tie 1 to SS will be this is 0, this delta PL2 is 0 and this is beta 2. So, it will become minus beta 2 delta PL1 divided by beta 2 plus beta 1. So, this is for frequency and this is for your tie power of putting those things. Now, now this one your what you call AC1 steady state value, right, is equal to delta P tie 1 to steady state plus B1 your delta FSS, this is the steady state value. Now, B1 is equal to actually B1 is equal to beta 1, right. So, is equal to delta P tie 1 to SS is equal to your this one this minus beta 2 delta PL1 upon beta 2 plus beta 1. So, here you put this one minus beta 2 delta PL1 divided by beta 2 plus beta 1, right, and similarly plus your this is actually B1 is equal to beta 1, B1 is equal to beta 1. So, here in this equation your what you call that your frequency, this in this equation you this delta Fs you substitute here, if you substitute you will find this is beta 1 and delta Fss is minus is there, that is why I am putting minus here, then delta PL1 divided by beta 2 plus beta 1 because B1 is equal to beta 1. So, that means if you take minus delta PL1 common, right, so it will be beta 2 plus beta 1 by beta 2 plus beta 1, it will be cancelled, it will become minus delta PL1, right. That is why here we are writing that ACE1 SS, after putting this is minus delta PL1, right, minus delta PL1. So, that means a steady state value you will find that value of the steady state value of ACS AC1 SS will become minus delta PL1. That means it will show some steady state error that is equal to the load disturbance in area 1 AC1 steady state value, right, in the case of uncontrolled mode. Now, similarly, if you make it AC2 SS, it is A12 into delta p tie 1 to SS, but A12 is minus 1. So, it is minus delta p tie 1 to SS plus B2 into delta FSS, and B2 is equal to actually beta 2, B2 is equal to beta 2, right. So, that is why I have put here B2 is equal to beta 2. If you substitute same expression, that means your this one, this is for delta FSS, this is for delta FSS, and this is for delta p tie 1 to SS. You can do it, simple thing, right, these two if you put it here and simplify, you will get that AC to SS will become 0, right. So, in the if the load disturb, that means what, if the load disturbance has happened in area 1, right, then it is showing that it is minus delta PL1, and if it is in your what you call in area 2, there is no load disturbance. So, AC to SS is actually becoming 0, right. So, that means from the above we can conclude that only the supplementary control action in area 1 will respond to delta PL1 and change generation so as to bring AC1 to 0. The load change in area 1 is thus unobservable to the supplementary control in area 2. The philosophy is that in area 1, that there, from the uncontrolled mode of operation, area 1 it is showing that it is equal to the load disturbance. That means supplementary control action in area 1, it should respond and it should bring this AC1 to 0, right. And whereas in AC to SS you have seen 0, that means the load change in area 1 will be completely unobservable by the your what you call supplementary control in area 2, because in the your what you call the disturbance in area 2, that is delta PL2 is 0, right. So, it will be totally unobservable because AC to SS is 0. So, that is actually your what you call or what I will say that steady state, from the steady state point of view. Now, suppose if B greater than beta, so if B is case 2, in this case, let us assume B1 is equal to 2 beta 1, that is your B greater than beta, and similarly beta 2 is equal, B2 is equal to 2 beta 2, and A1 to minus 1, follow the same procedure. In that expression of these two things. Whatever conditions are given, B2 is equal to 2 beta 2, A1 to minus 1 and B1 is equal to 2 beta 1, you put in this expression, you put in the equation 38 and 39, right. I am directly showing it, I am not because then I can save little bit of time, right. So, you substitute, very simple thing, just substitute and work out. If you do so, you will find AC1 SS will be your delta p tie 1 to SS plus B1 into delta FSS. That is actually, if you put those things, it will be minus delta PL1 into 1 minus 1 upon beta 2 will be there. And similarly, AC to SS, if you see, it will become minus delta p tie 1 to SS plus 2 beta 2 delta FSS is equal to, this will become minus delta PL1 beta 2. That means, if B greater than beta, this is not becoming 0, it is not becoming 0, and AC1 SS also is not becoming just minus delta PL1, it is 1 minus 1 upon beta 2, it is coming, right. So, that means that supplementary control action also in area 2 has to be responded, because although there is no load disturbance in area 1, area 2, right. So, that because it is coming some steady state value. So, that means here both area 1 and area 2 supplementary control would respond and correct your what you call the frequency deviation twice as fast, because we have taken B1 is equal to 2 beta 1, B2 is equal to 2 beta 2, right. However, the generation picked up by area 2, that means AC to SS is given minus delta PL1 upon beta 2, right, picked up will subsequently reflect itself as a component of AC2, right, and will be backed up again in the steady state. So, therefore, the LFC mode, for LFC load frequency control, the more logical choice of frequency bias setting is B is equal to beta, right. So, that is the most logical choice, but B cannot be less than beta, right. So, this is actually given you a question that why B cannot be less than beta. So, if you see the just a response for this area 1, area 2 and this thing, some for delta PL1 is equal to 0.0 per unit megawatt, right, and per unit megawatt, delta PL2 0. If you plot for example delta PG1, this is actually your what you call this case uncontrolled mode, you will find delta PG1 making 0.005, but not your what you call not 0.01 because it is uncontrolled mode. So, both the generation is what you call responding and generating power 0.005, here also 0.005 because it is uncontrolled mode responses of two area interconnector system, and tie line power if you plot it is showing minus 0.005, and this is the time, this is the response for your what you call your PG1, this is uncontrolled mode, that means U10, U20. If you make like this from MATLAB Simulink, if you put all these things you can easily see those what you call these responses. And if you put frequency not shown here, frequency also will show you the steady state error, right. Frequency here steady state error I made it here, this is time some minus 0.01176 will become the steady state minus only, right. So, that means your what you call that this is the uncontrolled mode response, these are uncontrolled mode response. Now, if you control, if you put the controller here, just if you put the controller here, then frequency your what you call frequency will be like this, this is your time, this is your this is time, and this is delta f, and this is 0, right. And if you so it is control mode, right. So, frequency will be maybe like this, it will go like this, it will go like this, finally it will settle to 0. This is frequency in area 1. Say area 2 also let me make use of another ink, area 2 also it will be go like this and go like this, it will go to 0, right. So, this is actually say this may be delta F1, disturbance is area 1, and this is also delta F2, right. This is frequency. If you see the generation, in that case of area 1 generation, say area 1 generation, so disturbance has occurred in area 1. So, this point is say delta PL1 say is equal to 0.01. So, if it is generation will be like this, will be like this, and finally settle to 0. This is your area 1 delta PG1, and area 2 case it may be go like this, maybe go like this, and finally it will come to 0. This will be your delta PG2, because this just I am drawing it from my intuition, but simulation will be something, right. Simulation also ultimately it will settle to 0, delta PG1, and delta PG2 will settle to 0, right. And tie power also this is your time, this is actually your time, right. And this is your what you call delta P tie 1 2. If you plot it, it will be like this, finally it will settle to 0. This is control. All these things are in control mode. That means that integral control action is there, right. With this your what you call this conventional part, all these things over. After this we will see a few numericals examples, and then little bit on deregulated system, and then we will come to unit commitment, right. Unit commitment actually something we will try to make it, because as you know that unit commitment is almost impossible to solve in the classroom, right, but little bit easier way we will make it. And I mean details not possible in this course, but some ideas, some thought we will get. But after this we will see the deregulated version in AGC, that is very simple thing, only little bit I will show you deregulation, just such that you can work out in the classroom only, right. Before that we will show some example, and after that we will move to unit commitment, right. Thank you very much.